In this talk, I would like to explore some of the wonderful applications of a mathematical object called a matrix. Now, I was originally going to call the talk The Wonderful World of the Matrix, but it dawned on me that some people might be thinking of another matrix. So instead, I'm going to call it What Are Matrices Useful For Anyway? It doesn't have the same ring to it, but hopefully, by the end of this talk, you'll have a new appreciation for just how versatile and practical those matrices that you heard about in your linear algebra course really are. So for those of you who aren't familiar with matrices or have forgotten what they are, let's start with the basics. What is a matrix? Well, a matrix is just a rectangular array of numbers organized into rows and columns. If there's a single row or a single column, we'll sometimes refer to a matrix as a vector. It's similar to a table or a spreadsheet, but rather than having labels for rows and or columns, we simply number them starting from the top left. And if you have an entry in that matrix, therefore it's easy to reference it, we just need to know the row and the column number. So for example, if we call this matrix A, then the entry A23 refers to the number stored in row 2, column 3. So why would someone care about matrices? Well, for most, the first exposure is in the high school algebra class when you're asked to solve a system of equations like the one here. And if after you've solved these equations enough times, you start getting tired of writing x and y in every equation, and you might start to recognize that you can actually just focus on the numbers in front of x and y, because that tells most of the story for the equations. And if you make sure that the variables are in the same order and you organize those numbers in front of the variables in a little table, what you get is what you might call a matrix. Now, we can also store the unknown variables x and y and the right-hand sides of these equations in matrices as well. And all we need is a way to combine them that's consistent with the original equations. And so one therefore defines matrix multiplication so that when you take, say, that first row of the matrix and you combine it with that matrix with the x and y in the middle, what you get is x minus y, which is precisely the left-hand side of the first equation. And the second row would combine with xy to produce the left-hand side of the second equation. So this way we can think of the left-hand sides from our original system of equations as just the product of the matrix of coefficients and the matrix of variables. And then the right-hand side is just, again, the right-hand sides from the original equations. All right, now this might not seem like much, being able to write a system of equations in matrix form, but it turns out it is incredibly useful. Well, for one, it makes it easy to write down on paper in the nice concise form ax equals b what the equations are. So here A represents the matrix, x and b are the vectors, or they're just single column matrices. And it may seem like that doesn't make a big difference, and that's true with two equations, it's not a lot shorter, but if you have 100 equations or 1,000, which is not as far-fetched as you might think, then this is a much more compact representation for the information. Secondly, this is helpful because it allows us to recognize that we can actually think about the collection of coefficients in the equation as its own thing. You can learn a great deal about the solutions to a system of equations just by understanding the structure of the coefficient matrix A. That can help us figure out whether we should expect there to be one solution or lots of them. It can also give us clues about how hard it's going to be to find those solutions and what methods might be practical for solving them. Third, it also allows us to expressing equations in terms of matrices and vectors also makes it much easier to get a computer to help you solve whatever problem it is that you're trying to solve. Computers are really good at dealing with organized tables of things, and they're really good at doing lots of calculations really fast, which can be a big help if you want to avoid solving a system of equations by hand. In fact, you can actually earn a PhD just by figuring out good ways to get computers to solve equations like these, because although it's not too hard to solve them when there are only a couple of equations, there are many practical problems where the standard techniques are impractical and you need clever tricks to get the solution you want. Why? Well, for one, real-world problems can be really, really, really big. I'm not talking about 10 by 10 matrices here, but rather 1 million by 1 million. That means that the matrices you're dealing with have 1 million squared numbers in them, or a trillion numbers in all. That can be problematic for lots of reasons. For one, memory is an issue. It's hard to process all that information without running out of memory, even on a modern computer. Second, speed is an issue. When you manipulate big matrices, you have to do lots of calculations, and that can take a while, especially if you don't take advantage of shortcuts like doing more than one calculation at a time or reusing the results of earlier calculations if you're having to do the same thing multiple times. And also, computers run into issues with accuracy. When they store numbers, just like your calculator, they don't store them exactly. they round them off after some number of digits. And so when you are combining matrices, each of the numbers in the matrix are off by some small amount, and that may not be noticeable for a couple of calculations, but if you do millions upon millions of calculations, those errors can start to accumulate and lead to answers that aren't very accurate. All right, so dealing with matrices and equations of this form ax equals b may not be quite as easy as it might seem, but it is important nonetheless. So at this point, we know that solving these sorts of equations, which we call linear because they describe flat things like lines and planes, is something that we can do, but it's easier said than done. But so far, what we focused on primarily is the theoretical side of things. We've got a lot of numbers and symbols and equations, but no clue what any of them are supposed to mean. And if you're turned off by this, that's okay. To be honest, I didn't love math when I was your age either. A lot of times it felt like pushing symbols around a page, and it wasn't always clear how those symbols applied to real life. However, what I found when I got to college is that math is not about numbers and symbols. That's like saying that literature is about letters or spelling. The symbols are not the interesting part. The interesting part is what you can do with those symbols. Those symbols are part of a language that allows you to express ideas and tell complex stories. As we'll see in a minute, even simple-looking equations like ax equals b can tell a remarkably complicated story once those symbols take on meaning. Second, once you become comfortable with the language of mathematics and you understand the properties of the objects that the symbols represent, you can start to use math as a powerful tool for solving seemingly impossible puzzles and making remarkable predictions about how the world operates. As an applied mathematician, that's what excites me the most about math today. So what I want to talk about in this presentation are 4 different types of useful problems that can be represented using an equation of the form ax equals b, where a is some matrix and x and b are vectors. For those of you with a little more math under your belt, you may recognize these 4 types of problems as 1. Linear systems of equations, where in this case we know the matrix A and the vector B, and we want to find x. 2. Linear transformations, where we want to find a matrix A that transforms a vector or matrix in some predefined way. 3. Iterative sequences, where we have some matrix A that allows us to compute a new vector xk plus 1 from an old vector xk. And lastly, eigenvalue problems, where we know the matrix A and we want to find a vector x that gets stretched by some constant vector lambda when I multiply by the matrix. Now, for those of you who are in a linear algebra course or will take one someday, you're going to learn a great deal about how to solve these sorts of equations. But that's not what we're going to focus on today. Today, what we want to talk about is primarily the application side and why these matrices and these 4 sets of equations are actually useful for things like building predictive models, image processing and animation, physics simulations or other simulations of real-world processes, and lastly, analyzing social networks. Okay, so let's get started. Our first application is building predictive models, and we're going to focus on equations that look like ax equals b. Let's start by considering a hypothetical scenario. Suppose that you're the manager of an ice cream shop, known for serving ice cream made fresh each day. Since spinning the ice cream takes a while, you have to have it ready before the evening rush. But at the end of each day, the leftover ice cream is going to get thrown away because it's not going to be the same quality the next day. This would cause you a problem. You need to know how much ice cream to make each day. If you make too much, it will go to waste. If you make too little, you'll run out. Either way, it's bad for business. So this is an example of a forecasting problem. You're trying to predict the demand for ice cream ahead of time. And these types of problems are faced by just about any restaurant, grocery store, or retail outlet you can think of. In fact, you could substitute making ice cream each day with ordering SKUs of product X each week, and the same issue would apply. So how would you solve a problem like this? Well, the first thing you might try is to collect some data. Record your sales over some period of time. So here I've got a plot displaying the sales from a real ice cream shop over an 8-year span. Now, if we wanted to come up with the simplest solution to this problem, what you might do is just use the average amount of sales for each day and make that amount of ice cream, maybe with a little extra just to be safe. So that's what the red line in the picture displays here. But you'll notice that there's a problem with this solution. The sales go up and down over the course of a year. And so for part of the year, it looks like you're going to have too much ice cream, and for part of the year, you'll have too little. It seems like there's enough of a trend here that we should be able to do better. What we need is a model, which would be some formula that tells us how much we should make each day. But how could we find that formula? Well, to start, you might need to have some explanation for what causes the sales to go up and down like they do in this data set. Any hypotheses? Well, the first thing that comes to my mind is that I tend to enjoy eating ice cream when it's hot, but I can take it or leave it when it's cold outside. So perhaps temperature is driving these fluctuations. So we could collect more data. If we look up the temperature on each of the days in our data set and add them to the table with all the sales, we could draw a graph of the temperature versus the ice cream sales. And what do you know? It looks like that when the temperature goes up, the sales goes up. And when the temperature goes down, the sales goes down. In fact, you might even imagine that there's some line going through that cloud of points that describes this trend. If we could figure out what that red line is, we could figure out that trend and use that to determine how much ice cream we should make. This is where matrices come in. What we want is an equation for a line that says, you give me the temperature and I'll give you the sales. The line is completely determined by its slope m and its intercept b. So we could set up a bunch of equations of the form m plus m times the temperature equals the sales, and we can write that in matrix form if you make a matrix which has a column of ones that correspond to the intercept and a column of temperatures, that's the second column, and multiply that by a vector of unknowns, our intercept b and our slope m. And then if we set that equal to the sales on each day, we would have a representation for all of those equations to try to get our predictions to match the observed data. So what we need is a way to solve that equation to find the appropriate amount of ice cream to make, and that is going to satisfy this equation, which is just ax equals b. Now, in this case, what you'll notice is that a is going to have as many rows as we have data points, which is going to make it hard to solve by hand. But a computer might be able to solve it. There's one problem, though. There's actually no solution to this system of equations. Maybe this shouldn't come as a surprise, given that we have hundreds of equations and only 2 unknowns. But there is actually a way to find the best solution that approximately satisfies the equation, and that is also expressed as a linear system. You can write down an equation A transpose, which is just the same matrix A turned on its side, times A times X equals A transpose times B, and that system of equations has a solution that represents the best possible line to fit through the data. If you take a little bit of calculus, you can actually show that that is indeed the case. Okay, so with the help of a computer, we should be able to find that line. Now, at that point, we can ask ourselves if we're satisfied with this model and its ability to predict the demand for ice cream. In this case, if you look at the picture, it seems like there's still a lot of variability. Sometimes the points are higher than the red line, sometimes they're lower, and maybe there's more we can do to try to explain what's going on here. So you might try to improve the model by adding additional information. For example, if you looked at the sales for each day, you might notice that the sales tend to be higher on the weekend, Friday, Saturday, and Sunday, than they are during the week. You can include that into the model by adding an extra column to the matrix, which indicates whether each day is a weekend or a weekday with a 0 or a 1. So if you add that and an extra variable w for unknowns that just represents the extra amount of sales we expect to get on weekends, then we can again get a matrix equation that can be solved using the exact same approach as the one before. In this case, you wouldn't actually get a line since you have 3 variables. What you get is what you might call a plane of best fit. And you see that there's sort of 2 groups of points. Points on one side correspond to weekdays, and the points on the other side correspond to weekends. And we have a linear trend aligned for both, but slightly different lines because we tend to sell more on the weekends. Okay, so now we can ask ourselves the same question. Are we satisfied? And if not, you can keep adding more and more information until we get to that point. If you decide to incorporate seasonal information as well, you might arrive at predictions that look something like the red curve that I've got here, which does a pretty good job of capturing the trend in the data. And in fact, if you compare your predictions, which I've plotted here on the horizontal axis with the observed values, you see that the line does seem to be a pretty good representation of the data points that we're observing, and for the most part the points are relatively close to the line. It's not perfect, but it's a lot better than what you would get with a simple solution like the average. And what that means is if we use the predictions from this model, we can better estimate how much ice cream we need to make, and that could mean big savings for a business. All right, so this is just one of many applications of the equation ax equals b, finding lines or planes of best fit, which is more formally known as linear regression. And these sorts of equations are also used in other contexts, like when people need to make decisions about how to best allocate their resources. They're also used as approximations to even harder problems that come up in a lot of physics, engineering, and science contexts. All right, so let's move on to another application, image processing and animation. In this case, our focus will be on what matrices do to other matrices when you multiply them and the uses of those operations for manipulating images and videos. The first thing to be aware of is that when you take a picture or video on your phone is storing that as a matrix. Each entry in the matrix is a number that represents the intensity of the color in a particular location. In a black and white image, we can use a single number for each location. Here, ones indicate that the pixel is white, it should be completely illuminated, and zeros indicate that the pixel is black, which means it's not illuminated at all. If you have a color image, on the other hand, then you actually need three matrices, one for the intensity of red, one for green, and one for blue. And by combining those colors in different ratios, you can actually represent any image with any colors that you would like. Now, if you have a video, you have even more data to worry about, because each frame in a video is an image. So you need three matrices for each frame, and most video has somewhere between 24 and 50 frames for each second of video. So when we talk about the resolution of a picture or a video, then that's talking not about the number of frames, but it's talking about how big are each of those frames. And it's a reference to the number of pixels or entries in the matrices that represent the picture. So one standard video format, which is typically called HD, has a resolution of 1920 by 1080, which means your images are 1920 pixels wide and 1080 pixels tall. And what that means for your video is that each frame is a collection of three matrices with around 2 million total entries in those matrices. So you can see why talking about big matrices would come up in these sorts of contexts. All right, so what can we do with these matrices? Well, the first thing you might want to do is modify them in some way to make them look different. You could stretch them, rotate them, crop them, you name it. And all of those operations that you associate with a photo editor can actually be expressed in terms of matrix operations. So let's suppose that we started with the image on the right here, which some of you may recognize as the main character from the 1999 sci-fi hit The Matrix. And let's suppose that we wanted to shrink that matrix down to make it half of the original size. Well, one way to do that would be to define a matrix with the locations of all the pixels. Let's call this capital X, and you'll notice in the first row we have all of the X coordinates of each pixel, so every dot in that picture has an entry in this matrix or a column associated with it. And then the second row is all of the corresponding Y coordinates. Now, if we want to shrink that picture down, we can accomplish that by taking a 2 by 2 matrix with the entries 0.5, 0, 0, and 0.5 and multiplying that by our original matrix. What that does is it just multiplies all of the X coordinates by a half and all of the Y coordinates by a half, and so all of the distances in the picture get shrunk down by a factor of 2. Okay, and so you see that result in the picture on the bottom left. We've got a picture that is about half the width and half the height of the original. And if you change the entries in that matrix that you use for the transformation, you can do all kinds of things like flipping the picture on its side or stretching it diagonally or any sort of operation that you might imagine. Now, this may not seem like much, but these sorts of operations are actually the basis of computer animation. If you first sketched out some image of a character and assigned coordinates to different key points in the image, what you can use is matrix multiplication to bring that character to life. So for example, here I have a little stick figure. If we put all of the points that correspond to his arm in a matrix X, and then we multiply that matrix by another matrix that describes rotations, so here's an example where I've got some sines and cosines, and then the angle theta here is just the amount that we'd like to rotate our picture, then the result of that matrix multiplication would be some new image where the arm has moved, it has rotated. And if you do this over and over again, then those movements accumulate and you get, well, why don't I just show you? See? He's waving at us. Now, once you understand that idea, building more complex movements amounts to just a bunch of little transformations. For example, down below, I've used 4 simultaneous rotations to make our friend do some jumping jacks. Now, obviously, I'm not an artist here. This is not all that impressive in terms of animation, but hopefully you get the idea that when you combine art with a dash of linear algebra, you can get some visually stunning computer-generated characters like the ones that you see in the movies. We can also do some math with matrices to fix damaged image. For example, let's say we're sending this image of our friend Neo over some noisy communication channel, and that some of the pixels get lost in the transmission. The result is what we have here in the middle. We have the same picture, but a lot of black dots where we've lost the information that corresponds to the colors that belong to that particular location. Fortunately, there is a fix to this. If we want to make Neo look normal again, we can zoom in closer at this picture, and you'll see that there are these isolated dots where the information is lost, and in the matrix, that is represented by individual pixels that have a number that's very different from the ones that's surrounding them. If we were to create a new image where you just replace each pixel with the median of all the values in its neighbors, in other words, if you take that matrix we've got at the top and we want to figure out what value belongs in the middle, well, we look at all the values surrounding the 0 and list them off in order from smallest to largest and take the middle one. In this case, since they're all 1s, the middle value would be 1. We would say, that 0 should probably be a 1, and we would replace that in our image. Well, the result of applying that process to the entire picture is the picture that we have on the right. And you see that it looks pretty much like the original. So this type of process where we randomly lose information can often be addressed by applying some statistical modifications to the matrix. Looks a lot better, right? Well, this is only the beginning of what matrix operations can do. They're actually at the core of the fancy filters that you apply to the selfies you post on Instagram. It's the basis for the techniques for dividing images into pieces and picking out faces that your phone does when you snap a picture. It even allows Facebook to do creepy things like look at all your friends' pictures and determine whether you're in them, and then suggest that you tag yourself in those pictures. So matrix operations are pretty useful for dealing with images and videos. That brings us to our third application, simulating physical processes. These sorts of simulations are often implemented by taking some vector xk, which represents the state of a system at a particular point in time, and then multiplying by a matrix A to get a new vector representing the state at some future point in time. Now, this is a little bit more complicated, so bear with me for a couple of minutes. But this comes up a lot in physics, where there are fundamental processes like the spread of heat in an object or the motion of a wave that are very naturally described by equations that have derivatives in them. So what's a derivative? Well, if you've taken some calculus, you might remember that derivatives are basically a way of describing the rates of change. How fast are things changing, like the temperature or the position of an object? And they're useful for describing pretty much any system that is changing over time. Now, we don't need to worry too much about the details of these equations today, other than to say that finding a formula for exactly what the state of the system is at each point in time can be quite difficult. In fact, for the most part, we only know how to solve these sorts of equations in a very few simple situations. And then even when we know how to write down the answer, those answers often involve really complicated things like adding up an infinite number of sines and cosines. As you might guess, that's a little bit difficult to use. Fortunately, linear algebra can help us solve these problems. All right, so before we look at the details, let's look at what the results of one of these simulations might be. So these 3 animations represent the solutions to the equations that I showed you on the previous slide. In the top left, we have a simulation of what's called the wave equation. If you picture that blue line that's moving as a guitar string that you just plucked in the middle, then this motion is just a representation of the motion of the string. Where here we've exaggerated the stretching, the displacement of the string in the vertical direction just a little bit to make it easier to see. And you see that you have these little waves that are traveling along the string and then bouncing back and so on. Now, in the top right, we have a 2D simulation of water waves. A very similar equation can be used to describe the motion of water on the surface of the ocean. And as you might guess from the complexity of the motion you see in the video, finding a function that describes exactly what the surface of the water is doing would be next to impossible. However, if we can try to frame this as a matrix operations problem, you can get a computer to crunch the numbers and get a good approximation to the behavior relatively quickly. Now, the last plot at the bottom is a simulation of the spread of heat through some medium. Here the color and the height indicate the temperature, and you see that initially there are some hot spots, but over time the heat just spreads out and evens out so that eventually the distribution of heat looks flat and smooth. So, how can we compute a solution like these? Well, the key insight is that you can often approximate these hard equations which have derivatives in them, which describe the rates of change, with much simpler equations that involve matrices that are just an approximation. So let's suppose for a second we wanted to know how the temperature of an object, like maybe the engine in your car, is changing over time. Well, there is some function, which you might call u, that describes the temperature at each location x. Now, the bad news is that we don't know what that function is. The good news is that we have an equation that physicists tell us can reveal how the function is changing. So if we imagine breaking that function up into little pieces, like you see at the top left, and instead of working about the values of the function at every point, focusing on the temperature at just a few points, x0, x1, x2, and so on, then we can replace this red curve, which has an infinite number of values at each corresponding to an infinite number of points, with a vector, which is what we have here in the middle. It is just the value of u at a finite number of points. Similarly, if you look down at the bottom, we've got this operation that represents a rate of change. You can actually represent that through a multiplication by a matrix, a particular matrix, mind you, but a matrix multiplication nonetheless. And so we can replace our unknown function with a vector, we can replace our rates of change with matrices, and so figuring out how the temperature should change over time can be reduced to essentially just multiplying by a matrix each time you want to figure out the future temperature. So if uk is the temperature at time k, and we multiply by a, we get the temperature at the next point in time. Now, this same idea of using a matrix equation to simulate the spreading process like we have for heat comes in handy in other contexts as well. That same exact equation describes how ingredients mix in a chemical process. It describes how the prices in financial markets change over time. It can even be used to fix a broken picture. So, suppose that our image of Neo was corrupted again during transmission, but this time instead of having random pixels that are removed, what we have here are whole blocks of mixing pixels. Can we fix the image to make Neo look normal again? Well, let's zoom in for a second on the color, on the missing bars. What we would like to be able to do is figure out what should those missing pixels be. Now, if you look at the missing bar and the pixels around them, you see that there is some information at the edges. If we can take that into account, we might be able to figure out what the black bar should look like and fill in the colors that are absent. So, how do we do that? Well, you can use heat flow to figure out what the colors in the black regions should be. What you need to do is imagine that each of the colored pixels around the boundary is like a little faucet that pumps colored ink into the picture. And that ink is just going to spread out and smooth out just like heat flows. And if you simulate that process with the same matrix equation that describes heat, what you would see is that eventually the black section would fill up with color, some parts would be light, others would be dark, and the color would depend on what the nearby boundary colors are. And if you do that process, then you can take that image in the middle with all of the missing information right through the middle of Neo's face, and you get the figure on the right, where those missing sections have been filled in, and it looks like Neo is relatively normal again. Okay, in fact, it's hard to tell that there's anything unusual with this picture at all, although if you do look closely, you will see that it does look like there's some smearing of the colors that doesn't look perfect, but it's certainly a lot better than what we had with the black bars in the middle. Now, if we were missing a really detailed section of this picture, then this process would not work all that well. But if the amount of missing data is small, then these sorts of techniques can do a remarkably good job of helping to reconstruct an image that looks similar to the one that you started with. These sorts of dynamic models that are based on matrix operations are everywhere in science and engineering. Whether you want to simulate a car accident, a hurricane, or a financial portfolio, the way to do that is to express your equations in terms of matrices. All right, that brings us to our last application, analyzing social networks, or any network really. Let's suppose that we have a group of people and we map out which people are friends. We might construct a graphical representation of those friendships, like the one on the left, where each person gets their own circle. Those circles are numbered from 1 to 7, and the dashed lines represent friendships. So person 1 is friends with persons 3, 4, and 2. Now, these pictures are great if you want to visualize a small network, but they don't work quite as well when you're dealing with networks of hundreds or millions of people. Fortunately, we can use matrices to represent that structure mathematically. We can define a matrix called an adjacency matrix, where each person gets their own row and column. If two people are friends, then we just put a 1 in the entry where those rows and columns intersect. Otherwise, we put a 0. So here, since lady 1 and guy 2 are friends, we put a 1 in the entries of row 1, column 2, and row 2, column 1. And since lady 1 and guy 7 are not friends, we put a 0 in row 1, column 7, and row 7, column 1. Once you've described the structure of the network with this matrix, you have all the tools of linear algebra at your disposal for uncovering information about the structure of the network. For example, if you work in marketing, you might be interested in determining who the influential people in the network are, so that you can get them to endorse your product. Is it her? Or maybe him? Or someone else? But how do you define importance? Well, you could just see who has the most connections. But often that's not the best way to go about this. After all, some people on social networks just try to friend or follow everyone they can. That doesn't necessarily make them important or influential. A better way to define importance is by observing that important individuals should have a lot of connections to other important individuals. That means that everyone's importances are interrelated. My importance depends on the importance of my friends, and vice versa. This idea can be made more precise by defining the importance of each person so that it is proportional to the total importance of their friends. If we define x to be a vector with the importance of every person in the network, then the total importance of their friends is given by ax, where A is the adjacency matrix with the 1s and the 0s that we talked about earlier. By our definition, this must be proportional to each individual's importance. In other words, ax must be equal to some number, which I'm calling lambda, lambda times the vector x of importances. Now, if you think about that, that equation seems like it might be impossible to solve. We don't know any of the importances, and this unknown importance shows up on both sides of the equation. To make matters worse, we also don't know what that proportionality constant is. It turns out, most of the time, if you choose the wrong value for that, you're not going to find any solution at all. In linear algebra, this is called an eigenvalue problem, and surprisingly, there are some clever methods that can be used to find both the vector x of importances and this proportionality constant at the same time. It doesn't seem like it should be possible, but if you understand the structure of the matrix, it is. Now, although this may seem like a contrived example, I should point out that these methods are not just useful for things like social media and social networks. They can be used to analyze networks where the influential individuals are people like him. In fact, agencies like the NSA use social network analysis to do things like identifying the leaders of terrorist groups or detecting terrorist cells from the network of contacts obtained through communication records. Both of these problems can be reduced to solving an eigenvalue problem. So, whether you work in national security or in the business world, analyzing the structure of complex networks can provide a great deal of valuable information. It allows search engines to identify the most relevant web pages to show you first at the top of the list when you type in a query. It allows the BCS to determine who the best football teams in the country are each year so that they can be selected to participate in the bowl games or the championship series. It even allows companies like Netflix and Amazon to provide you with personalized recommendations about the shows and products that people like you might be interested in. All right, well, that concludes my talk. I hope you come away with an appreciation for the fact that matrices and linear algebra in general are a versatile tool for representing data and for solving problems. Secondly, I hope that you picked up on the theme that often the way to make difficult problems solvable is to express them in terms of matrices. And finally, I hope that you have a new awareness of the fact that almost all of the products and services we use every day run on matrices. So if you want to understand how these matrices work and how you can go about solving these sorts of equations, like the ones presented in this talk, then you should definitely take some time to study in your algebra. And as Morpheus would say, find out how deep the rabbit hole goes.